All right, this is lesson 3, rates of change in tangent lines. Let's get started here. All right, a rate of change of a function. Rate as in ratio. Ratio comparing how much a y value changes when x changes by a certain amount. Being a ratio, we can write it as a fraction, so it is helpful to think of a rate of change as a fraction of y change over x change, which is what helps us to see that rate of change is represented by slope in a graph, okay? Function represented by the left pictured graph has a constant slope or constant rate of change. Slope is always the same no matter where you are. The right pictured graph is more interesting, however. The slope changes depending on where you are. That means the rate of change of y with respect to x is changing. What are the most common applications of this? There are lots of applications of this that we'll come across this year, but among the most common, suppose a function f represents position. The rate of change or slope in a graph of f would represent the object's velocity. Suppose you started with a function for velocity. If you were to graph that in turn, its rate of change would be represented by, or would represent acceleration. I also put in a little note here just to remind everyone, this comes up quite a bit this year as well. The word speed is related to velocity, but not exactly the same thing. Speed is the absolute value of velocity. In Calc A, we spend a good amount of time looking at the difference between the average rate of change and the instantaneous rate of change of some object in motion. Average rate of change is exactly what it sounds like. It's a measure of, on average, how much a function changes for a given fixed interval of x values, or in some case, t values, if your horizontal axis on a graph represents time. Instantaneous rate of change, on the other hand, is trying to measure the exact rate of change at a specific moment in time or at a specific value of x. This is something that's really hard to calculate with algebra techniques, and that's where calculus has come into play. You've seen this before. If we don't have the calculus techniques, the best we can do to estimate an instantaneous rate of change is to use an average rate of change. So let's go back to average rate of change, talk about how to find that. And average rate of change, the formula that we use for this looks very similar to the slope formula from Algebra 1. How do you find the slope of a line segment connecting 2 points? You might have learned it as y2 minus y1 over x2 minus x1. Here I write it as f of b minus f of a. That is a difference of y values over b minus a, which is a difference in x values. Okay. Graphically, I'm looking at this red curve here. There are 2 points identified at the left and right on that red curve. If I want to find the average rate of change or the average slope between those points, first of all, I recognize that the slope on the actual red line is changing as you move, but the average slope between those points is the slope of a line that directly connects those 2 points. It's called a secant line. All right, in example 3.1 here, just a basic example of finding an average rate of change. To do this, you need to know what function we're dealing with. We need to have a fixed interval of x values to plug in, right? So here's me applying the formula. We are going to plug in the ending location first. So I'm plugging in e to this function. I'm plugging in 1, and then I'm subtracting. And then there in the denominator, you see me simply subtracting the x values and I'm working it out. That's a really basic, simple example. In theory, an Algebra 1 student could do that. Example 3.2 puts a little context in, more of a word problem. It's also quite common in this course to have information presented in a table. In this case, we don't have an actual function provided for x. X is supposed to represent a distance between the puppy and Maya, or at least in the direction of this other character, Theo. But we don't know the function for x. Instead, we have specific values of x provided corresponding to certain time values. So with this sort of information, whoops, yes, we can still find an average velocity because again, you don't really need to know the actual function for x if we're already giving you the values at the locations we want. So if I want to go from 0 to 2, I take x of 2 minus x of 4 over, or excuse me, sorry, x of 2 minus x of 0, which is 4, over 2 minus 0. It's a little confusing in this example that what used to be the y values in the graph are being called x here, but it's something we'll just have to get used to, being really careful what different variables represent. Also notice we should always put some indication of units on answers where units are applicable. Here's another quick example. I want to go from 3 to 6. So we check out what is x doing at 6, what is it doing at 3, put it over 6 minus 3, we get an answer. Now, the third question here is a little bit different. This does not say find average velocity. It says estimate velocity at a single moment of time. You do not have an interval here. You have a single moment in time, and yet we are unable to exactly figure out a velocity at t equals 2 from a table. So even though this is a different question, the process ends up being the same. What I'm going to do here is I'm going to pick two time values as close to t equals 2 as possible, one on either side. So of course that would be looking at t equals 1, t equals 3, and then just apply your slope formula again, your average rate of change formula, to get an answer there. All right, moving along, let's start looking at instantaneous rate of change. How do we find this? What are the calculus techniques that allow us to actually find the rate of change at a specific moment in time as opposed to an interval? There's a lot going on here. Try to paraphrase, but you could always pause the video and read this to go at a little slower pace. Basically, the setup is, again, I have a curve with slopes that are changing. I identify a couple points of interest, and I could even draw in a secant line to get a starting estimate of the average rate of change between those points. But then what we want to do, imagine taking the rightmost point and sliding it closer and closer to the first point along your curve, just for the sake of a visual. Maybe eventually I slide it to this location that I'm drawing in here. And as you slide that point, the secant line is also changing, its slope is changing, but the idea is that the closer and closer you get to the starting point, the closer and closer your secant line slope gets to being just the actual slope at x comma f of x. So we're basically saying, let's calculate the slope formula, or rather the limit of the slope formula, as the distance between our 2 points approaches 0. All right, I'm going to pause for a second. All right, I just got interrupted and I paused the video for a while, so I've kind of forgotten exactly where I left off. Sorry. I think what I was saying was instantaneous rate of change. We think of it as the limit of the slope formula from algebra. I know this doesn't look exactly like the slope formula we saw earlier, but it is when you describe your first and second points the way I've done in this picture. Instead of y2 minus y1, I've got f of x plus h minus f of x. And of course, h is just the horizontal distance between my x values. Meanwhile, in the denominator, x plus h minus x does simplify down to h. So as that distance horizontally between my 2 points gets smaller, 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 this limit will give you the instantaneous rate of change. Okay, now you've heard of another name for this in Calc A. If we simplify this limit, the expression that results is considered a new function, and that's called a derivative function. So when we find derivatives, we're finding functions that tell you the slopes or instantaneous rates of change of a function at specific locations. For a given f of x, the notation f prime is sometimes used. We'll see other notations as well. All right, so let's start scrolling down here. There's an alternate limit definition for derivative. It still involves the slope formula. It doesn't involve h being used to describe anything. Instead, imagine just an a comma f of a, x comma f of x. Imagine the x f of x sliding closer and closer towards a comma f of a. Think of this leftmost point as being fixed. So as x approaches a, here's your slope formula. This one actually looks a little bit more like the conventional slope formula from algebra. Other notations for derivative. F prime works, but it's actually not considered the best notation. It's not quite as descriptive. My favorite would be the one that I am hovering over here, or other versions of it. dy dx is considered better because it successfully communicates what you're taking the rate of change of and what other variable it's with respect to. dy dx is derivative of y with respect to x. df dx behaves similarly. Here's yet another way to write that. You should be familiar with all of these. All right, moving along. Rates of change, slope, derivative, tangent lines. There are several ways to communicate the same idea about rates of change. We see that even in just the notation for derivative. It reminds us again here, all those phrases above all mean the same thing. Well, now I'm going to introduce this concept of a tangent line, and I'm going to again show you a lot of different ways that tangent lines are referred to in this course. So tangent line, imagine a specific point on a function. A tangent line is a line that intersects that point and has the same slope as the slope at that point. So here we've got this red curve whose slopes are changing as you go. But if I focus on one single point, there's a particular slope that's occurring right here. If I imagine a line that has that constant slope, that would be the tangent line. It touches a curve at exactly one point. And there are a lot of different ways that tangent lines are referenced without actually always saying the word tangent line. So all these phrases here are talking about the same thing. Slope of a tangent line at a certain point, slope of a curve at that point, slope of y equals f of x at x equals a, instantaneous rate of change. All these things refer to the slope of that tangent line. Okay, the derivative of f at x equals a is the same as the slope of the tangent line. F prime of a, same as the slope. So just be wary of that. It does happen sometimes where students come across problems that they knew how to do them, but they have struggles because they didn't understand exactly the wording. So that's on you to make sure that you're aware of all these different ways to phrase that. All right, example 3.3, here is me reminding you how to actually work with the limit definition of derivative to find a derivative. I'm fully aware that if you made it through Calc A, at some point you learned shortcuts, and 99% of the time you use the shortcuts, but every year on the AP test, there are a couple questions designed to make sure you can either use or recognize the limit definition. So this is not something you can just forget about now that you know some fancy shortcuts. So here's just me working through f of x equals 2x squared plus x. I want to find the derivative the long way. I am really just plugging directly into the formula that we saw a couple slides ago, the f of x plus h minus f of x over h, and then I'm taking the limit. So I'm literally replacing these x's with x plus h. Okay, so here's what it looks like when I take that f of x and I replace my x's with x plus h, and then I subtract the conventional f of x, that part's easy, divide it all by h. You do have to show limit notation every step of your work up until you evaluate that. But what I'm going to do first before I evaluate anything is I'm going to clean this up. So you can see I've multiplied out everything. And from the first step, I'm looking to cancel terms. For example, here's an x and here's a minus x. Those cancel out. That's kind of nice for us. What else? 4x h2. Oh, yeah, the 2x squared and the minus 2x, right? Once you've simplified that down correctly, you should be lucky enough that you get some nice cancellation. If I take every single term in the numerator and divide by h, here's where I end up. And now I'm at a place where I can evaluate that limit. So I kind of glossed over the fact that I was unable to evaluate it first because you can't plug a 0 directly in for h in the denominator. That's problematic. That speaks to maybe some kind of discontinuity. All right. We continue this example on the next page. At this point, however, we've already established what is the derivative of the original function, so I can confidently say f prime equals 4x plus 1. Once I have that information in front of me, there are various questions I can now answer fairly easily. Be careful. Some questions are still, I would classify as algebra questions. Part B, for example, what is the y coordinate when x is -2? That's an algebra question. I don't need the derivative for that. If I want to find y coordinates, I plug x directly into the original function f of x. Part C, however, says what is the slope of the graph when x is -2? For that, I plug my x value into the derivative. The derivative's job is to give us slopes of graphs or rates of change at specific points. Equation for a tangent line. This is something that honestly comes up quite a bit in free response questions, and it should be easy. The thing to remind yourself of is that point slope form is usually the easiest form in which to write these equations. All you need is a point and a slope. We have a slope already. We have a point already. -2, 6 is the point that occurs when x equals -2. So y minus the y value equals slope times x minus the x value. In this case, it looks like x plus 2. That should be easy peasy free points on an AP problem to put together a tangent line. You do not have to simplify that at all. Don't waste time moving this into slope intercept form because you're wasting time and you're also risking making silly mistakes. For what values of x is the rate of change positive? This maybe a little trickier, but if you think about it, it's not too bad. I already have an expression that describes the rates of change at any x value I want. So I'm basically asking, when is this expression, 4x plus 1, going to be greater than 0? That would be positive, and then I just solve out that inequality. Real quick, this last part thrown in here, I'll be honest, this does not show up a ton. Normal lines are lines that are perpendicular to curves. They are still pretty easy to put together because you take essentially the same equation as your tangent line, you just make a perpendicular slope, which is opposite reciprocal slope. Everything else has stayed the same. Okay, example 3.4. Here's another one that gives us a function to start with. We're supposed to find an equation for dy dx. Now, this one does not actually say that you need to use a limit definition. So unless it tells you you have to do that, I would say, yes, you should use shortcuts. So if you're able to determine the shortcut for this function here, you might think of it instead of as 1 over x as x to the -1, and then you can apply your power rule shortcut. That would have been fine here. I did choose to show it the long way just because I wanted another example of the limit definition, but this time using the alternate limit definition just so you can see what that might look like. So here's me doing f of x minus f of a over x minus a, and then still going through some algebraic steps to evaluate that limit. But if you did it with a shortcut, that's fine. Example 3.5, I threw this one in here because this is another fairly common multiple choice question on the AP test where they don't come right out and tell you that you're looking at the limit definition of derivative, but they do expect you to recognize it. That's one of the ways that they test you to make sure you know the limit definition. So it might just say, hey, here's the limit, figure it out, right? But if you look real closely, you see, oh, there's an h going to 0, there's an h in a denominator. The numerator has some function involving a number plus h and then subtracting something else. So all those pieces are lining up to convince me that this is really some variation of that limit formula, which I'm writing out here. Okay, so at that point, it's just a matter of figuring out what are the different pieces. For example, the x plus h, it looks like we're plugging in a 9 for x. Here I called it a, but it's essentially the x value. We're interested in plugging in a 9. Now, what operation is actually being performed on x plus h. If I can figure out what I'm doing to x plus h, that'll give me an idea of what function f is supposed to be. And of course, it's plain to see that the operation on the 9 plus h is a square root. So in general, I now know that the f of x that they're referring to is a square root function. When I write that out, I'm not going to write a plus h, so I want to keep it more general. But yeah, square root is the function involved. Honestly, at that point, you're probably going to go to shortcuts. I would almost say disregard all my work in part C, because I would expect you to use shortcuts here. Okay. But the idea is we've recognized that this is a limit definition. I already know from Calc A that this limit definition is the same as derivative. So this mess up here is just a fancy way of saying, hey, find the derivative of square root of x and then plug a 9 into it. So as soon as I've established root x, here's me doing a shortcut to find f prime. I clean it up a little bit, and then I'm just plugging in a 9 where I see an x, and that's my answer. I really, really like those problems. They're kind of clever. It's very satisfying when you see what they're doing and you figure it out. Final example is a similar kind of thing. It's just this time we are seeing a version of the alternate limit definition. So just to write that out again, this is the one that's f of x minus f of a over x minus a. These are a little easier in my opinion because right away we know that the first term in the numerator is the actual function we're dealing with. So this is a fancy way of saying, hey guys, find the derivative of 3 over x and then plug in a 1. So that would be the quickest way to get through the problem. Over here on the left, here's g equals 3 over x. Here's me using a shortcut to find g prime, and then I'm going to plug a 1 into, well, into whatever I get back. Okay, so again, you don't really need to do it the long way like I show in part C here. All right, guys, thanks for watching. You know the drill. Shoot me an email or ask me in class if you have any questions. Thank you.